So now we'll continue our discussion of ray diagrams to show how optics work. This time we're going to look at lenses. The two types of lenses, of course, are converging or a convex lens and a diverging or concave lens. So here's a convex lens, and of course it's curved on the outside, and there is an imaginary line that goes from the top to the bottom of the lens. And as we draw that line, that's where we'll do any changes. When a ray goes through the lens, we'll say that it changes at the center, even though ideally, or in real life, it actually changes when it hits the lens. But to keep things simple, we'll just look at the changes at that center line. Now, of course, we have two focal points. There's one on the front and one on the back. This is the real focal point, and this one here is the virtual focal point. And we use both of those in determining where the image is going to be. So, the two focal points, and then, of course, ray 1, from our object, we draw a line parallel to the principal axis, and it refracts through the lens, as you can see at the center, and goes through the real focal point. So that's line number 1. Line number 2 will go through this focal point. It will go down, and then when it hits the lens, it will refract parallel to the principal axis again. And there you see it. All right. The third line is very simple to draw. All we do is draw it right through the center of the lens, and it doesn't move at all. All right. So when we take those three rays and match them up, then we see that they intersect beyond the lens, and it looks like the image is going to be upside down. That makes it real, and of course it looks like it's about twice as big, so it's going to be inverted, larger, and real. And this would be the kind of lens that you would use if you were a far-sighted person. All right, here's a diagram of a far-sighted eye, a person with far-sighted vision. Their normal lens will put the object beyond their retina, which is at the back of the eye. So what we do is we use a convex or converging lens in front of their eye. That condenses the rays just a little bit so that now they meet right at the very back of your eye. So right at F, you see that you won't see an image because both the rays, the one that goes parallel to the principal axis and then through the focal point, and the ray that goes through the center of curvature, both of those are going to be parallel. And of course, a ray that goes straight down will just go right through F and won't intersect those lines either. And so an object at F doesn't actually show an image at all. All right, an image at infinity, or in other words, you never see it. And an object that's between F and 2F, well, that looks like it's going to be a little bit bigger, and of course it's real. All right, and of course if you go for a slide projector, works that way. An object right at 2F, well, it'll be exactly the same size, only upside down. So at the center of curvature, in other words 2F, you will have an image that is exactly the same size, only upside down. And beyond 2F, of course, we see that the object is still real, but now it is upside down and it's smaller. All right, the image appears between F and 2F is smaller. All right, this is how it works in your camera. And there's an object that's inside of F. Of course, this is a special case, and this would look, all right, if we connect those lines, we can see that that particular object appears bigger. And that's often how we use our convex lenses, to look at things close up. So we put the lens very close to the object, and then as we look through it, through the lens, we see the object that is going to be right side up and much larger. So many magnifying lenses are used so that you put the object actually inside the focal point, and then you get a larger right side up image. It's right side up, so it's virtual, but you can still take a look at it. Okay, upright, larger, and virtual.